Hello, everybody. In this video, we're going to return to our discussion about black holes. We are now armed by a little bit of understanding of Einsteinian relativity, which allows us to do one final fun thought experiment. What happens if you fall into a black hole? What would you observe? Or if you're on a spaceship and you have some sort of enemy out there and maybe you just, toss them out a little bit, what would happen to that person as they went to the black hole? Or maybe I always like to have a positive spin on things. Maybe it's you and a friend and you want to do this wild experiment and your friend volunteers to be the person that descends into a black hole and they're going to be sending you reports back about what they are observing. And then that way you can observe your friend falling into a black hole and your friend can observe what's going on with you. What are the observations that are made? What do we know? What don't we know? And we are now equipped with our ideas of relativity to be able to handle this question. Let's go ahead and dive in. This is more fun material than rather official course material. So if you don't retain any of this, you should be fine for the final exam. If you do retain this and have questions, make sure you post in the week 14 discussion. But let's go ahead and jump in and see what's happening with falling into a black hole. And one of the things we should talk about is the curvature of space-time itself. Remember that special relativity tells us that space and time are connected. So there is this idea of space-time. We have 3 spatial dimensions plus 1 time dimension. And then we saw that mass actually warps space-time. So let's take a look at how extreme the warping of space-time can get, because it's really how extremely warped space-time gets around a black hole that really causes our breakings of physics, although they're not really breakings of physics. So one of the first things we need to keep in mind is that the more massive and the denser an object is, a mass is, the more space-time is going to be warped. So if we're going to say, look at the sun, yeah, it is a pretty massive object and it's quite dense. So it does warp space-time fairly significantly. White dwarfs have about the same mass of the sun, but it's really compact. We've jacked up the density. So they really cause a steep curvature in space-time. And here we're sort of adopting that sort of trampoline model. But if you really wanted to think about this, you wouldn't be warping a 2D surface. You'd be warping 3D space-time. But the idea still stands, and it's a good model to have in your head. By the time you get to a neutron star, you have distorted space-time so much that you really need to start accounting for relativistic effects. You have to account for relativistic effects in pretty much all these cases, but you really aren't going to understand the space-time around neutron stars accurately at all without really accounting for relativity. And then by the time we get to a black hole, things get weird. As we reach the singularity, any concept and any meaning of space-time breaks down. Some people say that this is a rip in space-time. That's not really a good way to put it, because space-time isn't something you can rip. It's more that space-time can no longer be defined. It's not really a thing you can talk about, which is stranger and hurts my brain more. So a lot of times people really do just stick with the rip, but I want to encourage you not to take that fallacy forward. That it's not a rip in space-time. It's more that our current physics runs out of a way to describe what space-time is anymore. So, and as you cross the event horizon, the space becomes so stretched out that nothing can traverse that crazy stretching of space. Not even light can traverse it, which actually gives us the name for the event horizon. Since nothing can traverse what's inside the event horizon to outside the event horizon, not even light itself, then that means that any events that are happening inside within the event horizon have no effect on anything that's happening outside of it. So all of the events within the event horizon are self-contained and unobservable from outside. It really is a horizon of events. Okay, so now we know that space-time is crazy warped around a black hole. So what would happen as you start descending this deep gravity well, this warping of space-time, this extreme curvature of space-time, as it's getting stretched out due to the incredible mass compacted or shoved into a tiny space? What would happen as you approach it? what would your if you were approaching it, what would you if your friend was approaching it, what would you see happen to your friend, and what would your friend report back as to happening to you? First, let's observe something falling in. So now your braver than you friend decides they volunteered, like, yeah, I'm definitely going to jump into that black hole. I'm going feet first. Better than head first, I think, in this case. So, what would happen as that person fell towards the black hole? And I want to break this down into just a couple of the effects. So, we'll start with gravitational time dilation. Remember, the deeper you go into a gravity well, the slower your clock would run. So, the further down your friend falls into this gravity well, and deeper into the curvature of space-time, the slower their clocks would run. And as you get closer and closer and closer to the event horizon, that time dilation becomes larger and larger and larger. Your friend's clocks run slower and slower and slower. If they were, say, sending you an electromagnetic pulse, both in radio waves, so it would make a chirp that you could hear inside of your spaceship where you're safely watching this, and simultaneously send a laser pulse, invisible light, so you could see a blink of light when as they go in. If that was set up to send a pulse every second as they get closer to the black hole, you would hear the chirps. As soon as they leave, it would be chirp every second, and then as you get closer to the black hole, it would be a chirp every 1.1 seconds, every 1.5 seconds, every 2 seconds, every 3 seconds, every hour, every couple of minutes, every couple of hours, every couple of days, slower and slower and slower. And you would see the pulses of light reaching you. They would happen at longer and longer intervals because the clock for that person that's falling into the well is slowing down. So you observe their time slowing down. If they were trying to wave at you the entire way down, they'd be waving, and then you'd see the wave getting slower and slower and slower as they go further and further down the gravity well. As they get to the event horizon, when they get to the event horizon, time dilation gets stretched out to an infinite dilation, which is a mathematical way to say time stops. So you would see this person following towards the black hole, the event horizon of the black hole. Their wave at you would slow down. The radio chirps would get longer and longer apart until they would go forever silent. You'd hear that last chirp, and it would be a infinite amount of time until you hear the next chirp. It would be forever until the next chirp comes, which means that the next chirp never comes, and the next laser pulse never reaches you. Now, this is quite strange because if you're watching this person, they would fall, and sure, it would take a really, 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 really long time because to watch them fall because they're moving slower and slower until they hit the event horizon. But when they hit the event horizon, time would stop. You would never actually see this person fall into the black hole. They couldn't make it. The time would have stopped, so you can't see them fall into the black hole. Weird. Okay. All right. Now, that's assuming a couple of other things. And there's an additional problem that sort of resolves this as well, because we would not see your friend falling well before they get to the event horizon, because we also have to account for gravitational redshift. I didn't introduce this as one of the consequences of general relativity, but might as well introduce it now. So gravitational redshift is redshift, kind of like we talked about with Doppler redshift, but what's stretching out the wavelengths now is not speed, not the motion of an object, but the stretching of space-time itself. So as space-time gets stretched out, so is the wavelength of light. So the more that the space is stretched, the longer the wavelength of light will become. So now let's go back to those radio chirps and the laser beam that they're going to be sending at you. So when they first fall out, you hear the radio chirps and you see the flash of light, and say they're shining a blue light at you. As they get closer to the black hole, the chirps slow down and you have to adjust your radio receiver to longer wavelengths of radio waves, lower frequencies, so you can still hear the chirps. The laser beam shifts from being a blue light coming at you to, say, a green light, to a yellow light, to an orange light, to a red light. As they get closer and closer and closer, you dial your frequency to lower frequencies so you can hear the radio chirps, really, really long radio waves. And eventually the laser pulses aren't invisible light anymore. You have to put on some infrared goggles so you can see the light coming to you, because now the wavelengths have been stretched out and it's an infrared light coming at you. And you can keep playing that game until you reach the event horizon. And as they've reached the event horizon, this gravitational redshift would stretch the light out to have infinite wavelength, which would not be light. It would have zero energy photon, so it's no longer light. And that's just with the laser beams and the chirps. I mean, the laser light, you can imagine, okay, you observe it in the visible spectrum, and sure, it turned red. That's weird. All right, got to put on my infrared goggles. That's strange. Then you have to go from your infrared goggles, your microwave detectors, and now you can use your radio receiver again to see the light, the visible light that they think they're sending at you. And eventually that would disappear as well. But think about it. How would you actually observe if you're watching this friend fall in? Any of the light that is reflecting off of them and coming to you is getting stretched out as well. So you'd be watching them and they would turn red in color, and then they would fade from view going into the infrared. So you have to watch them in the infrared, and then you'd have to watch them in the microwave, you'd have to watch them in the radio. And eventually, even the light that's reflecting off of them would get stretched out to infinite wavelengths. So they would disappear from view. This is super weird stuff. This makes my brain hurt. And every time I talk about this, I spend a lot of time looking up all this stuff, just try to make sure that what I'm saying is sane. And yes, these are the consequences if you follow what our physics say. There are likely, physics doesn't really like breaking, so there are probably some slippery way that physics gets around these when we actually consider what's going on. But this is, as far as we know right now, we have sort of these weird paradoxes. You'd never see them fall in, and then their light would disappear. All right. So I've already said all of that. Now, let's consider something else. What would they physically look like? Would they stay exactly like they are? You have probably heard of this phrase called spaghettification. And this is not good for your intrepid friend who decided to be the volunteer to go into the black hole. Because as they get closer to the black hole, as they're approaching the event horizon, we have to consider the tidal force. It's what causes tides here on Earth. And it gets pretty extremely strong near a black hole. Let me just briefly describe the tidal force. And we'll use the falling into the black hole. So your friend's going in feet first. The feet are a little bit closer to the singularity, assuming there is a singularity. They're a little bit closer to the black hole than the head is. And remember that gravity gets weaker with the distance squared. So gravity would be pulling on your friend's feet stronger than it's pulling on their head. So that gradient of force of really strong at the feet and getting weaker towards the head would stretch your friend out. It also would compress your friend from the sides. So as they get closer and closer and closer to the black hole, their feet would get stretched out. They would be elongated and compressed, turned into a noodle, turned into like a noodle, a spaghetti noodle. Hence, we call this spaghettification. Now, that's a very ideal sense. I mean, eventually the feet would pop off and you'd be torn to bits. And then those bits would get spaghettified. But that's a little bit grim. Let's just imagine spaghettification. Well, you have to really think what's going to happen, because eventually things are going to get stretched so thin that it's going to actually rip all the molecules that you're made of apart, and it's going to turn you into atoms, and those atoms are going to rip down to the fundamental particles as you get stretched to be infinitely long and infinitely thin, whatever that means. Maybe that'll help you sleep at night. I'm not sure. But you get spaghettified. Things get spaghettified as they fall into the black hole. And yes, we actually observe this happening. I'm just going to go back here. This is an artist's rendition We've seen several stars get spaghettified now. We've only been observing this for a few years where we've actually been able to detect these things. But we have observed spaghettification of stars as they get ripped apart as they're falling into the supermassive black holes at the hearts of the galaxies that they live in. And this is an artist's conception of that process. So you can see this material is getting spaghettified by extreme tidal forces associated with extreme stretching of space-time near a black hole. All right, so now that we've figured out what happens to your friend, poor friend, they were brave. Thank you for your service to science. Well, let's consider the reports. I'm sure it might take you an infinite amount of time to get all the reports back, so you could see what they saw. But what would your friends see as they're falling down towards the black hole? Say if they look back towards you and fell backwards into the event horizon. So again, let's go with gravitational time dilation. As they get deeper into the gravity well, their clocks are going slower. So it looks like you on the spaceship, now you are just zipping around super duper fast, according to them. You start moving at ridiculous cartoon-like speeds. It's like if you're watching this video and you set it to 2 times speed, 5 times speed, 10 times speed, 100 times speed. And then as they fall closer and closer to the event horizon, that time is speeding up to the point where you would see them as their time stops. What would happen is they fell through and crossed the event horizon? Well, time would outside be going infinitely fast at that point. So it's theoretically predicted, no way to actually check this, but as you fall into an event horizon, if you weren't spaghettified and you could actually see and things like that, then you would see the entire future history of the universe play out instantaneously as you crossed the event horizon. Because time is running infinitely fast, so you'd see everything, the entire future of the universe play out in front of you. But it all happened in an instant. And as you fall, it'd be getting faster and faster and faster and faster. Some really strange things. So if you want to watch the entire history of the universe, go find yourself a black hole and jump in. Don't get spaghettified on the way down. All right, so other strange things. Let's imagine that somehow you can protect yourself from spaghettification, you can survive, and you enter the event horizon. Something strange happens, and this is where Einstein's equations do still work within the event horizon, and they predict that all of a sudden, you've collapsed down to there's only one direction now. Just like time can only move forward once you're inside the event horizon, there's only one way you can move in space, and that's towards the singularity. So we've now collapsed to, well, there is still direction, but there's only one direction, and that's forward towards the center of the black hole, towards the singularity, if it is a singularity. Okay, so that's what would happen if you fall into a black hole, but I would be remiss in my duties if I didn't share with you some of the crazier theoretical, as in this, the mathematics works out, these can possibly exist. So people get really, really excited about these. But with the extreme stretching that can happen around black holes of space-time, maybe there's a part of space-time that folds back around on itself. And then with these extreme curvatures of space-time, you could have 2 points, basically make a bridge between them. And if you've watched movies, this is where they always take a piece of paper and then they fold it in half and punch a hole in it and say, well, if you wanted to go from here to here, all you'd have to do is bring the points closer together and then you can go straight through the paper. What they're trying to describe there is what is called an Einstein-Rosen bridge, where you would have an extreme warping of space-time here, perhaps caused by a black hole, and over here in a different part of space-time, you have an extreme warping of space-time caused by a black hole. And then those two things connect in what they call the throat, and they make a bridge from one part of the universe to another part of the universe, sort of a cosmic shortcut, because space-time is somehow folding around back on itself, and you can punch a hole from one part of space-time to another part of space-time. Now, you might be thinking, Dr. Lindsay, that sounds an awful lot like this idea of a wormhole. And yes, the formal name for a wormhole, sci-fi fans rejoice, is an Einstein-Rosen bridge. These are allowable by Einstein's relativity equations, but they're only theoretical. We've never observed these things. We don't know how to observe these things. We don't even know if they could physically exist, because to cross that barrier to go through the throat, you would have to have some weird things happen with energy going on. So theoretically, these are possible. I want to be careful here, though, because just because they're theoretically possible doesn't mean, like Dr. Lindsay said, there's wormholes out there. We have to await for the evidence. Just because our current physics has mathematical solutions that allow it doesn't mean that's reality. That'll be my final science lesson, astronomy lesson for you for this semester. I hope you've enjoyed all the videos that I've sent your way. I hope you've enjoyed this class. Thank you for tuning in. For all of you that have watched all of these videos to the final end, you have my deepest thanks. And hopefully I will see you sometime in the future.